Welcome folks! In this video, we'll be taking another look at the example given in section 3.2 of two moving point charges. We'll examine how the forces change as we change frame, and the implications that this could have when the particles are set to have the same speed, or the more general case where the speeds can vary. We'll also briefly discuss the principal differences between this situation and the example given in 3.1, that of an electron attracted to a neutral wire. First, let's focus on the two charges travelling at some equal velocity, which we'll call u. We established in the notes that in the frame S', which is travelling with the two charges, the force can only ever repel, given that the electric force is the only force present. We're interested in knowing if there is a speed u in frame S at which the magnetic force would dominate. If so, then the charges will attract, and if not, the charges will repel, as in frame S'. The former case would present us with a paradox, where the charges repel in one frame and attract in another, apparently defying the laws of physics. So, let's dive in. Using the formula 3.2.3b from the notes, we separate the electric and magnetic components of the force and rewrite them, setting the magnitude of the magnetic force to be greater than the magnitude of the electric force. We cancel out the similar terms on both sides to get an equation in terms of r, u, y, c, and k. Rewriting r and u, we get the final equation, where r is decomposed into its linear sum. From there, we take the magnitude of both sides and rearrange the inequality to get u over c is greater than x squared over y squared plus 1 to the 1 over 4. Since x and y are both greater than 0, the square of x over y must also be greater than 0. Therefore, the square of x over y plus 1 to the 1 over 4 must be greater than 1. This finally means that u over c must be greater than 1. Hence u must be greater than c, the speed of light, which is evidently impossible. Therefore, we can conclude that in this first scenario, the total force is repulsive, as there isn't a velocity u at which the magnetic force dominates. Phew! One case down, one to go. Let's keep moving. Now, we look at the more general case, with two charges travelling at different velocities, to see if there is a speed for either particle at which the magnetic force dominates. The derivation is slightly more difficult, as the formula for the total force is more complicated. Following the same steps that we did previously, we reduce the net force to its electric and magnetic components, and we see that the magnitude of r must be less than the magnitude of 1 over c squared v cross u cross r. Taking u cross r gives the expression minus zu times the unit vector j plus uy times the unit vector k. Then, using the definition of the cross product and simplifying the expression, we get vu root z squared plus y squared times sine phi times the perpendicular unit vector n, where phi is the angle between v and u cross r. After plugging in the results from the previous slide, taking the magnitude on both sides, and squaring the inequality and rearranging it, we get a result of x minus ut squared over z squared plus y squared plus 1 is less than 1 over c to the fourth times u squared v squared times sine phi squared. For simplification, we make two substitutions. Firstly, we define alpha equal to the left-hand side of the previous inequality. If x minus ut squared over z squared plus y squared is always greater than 0, then x minus ut squared over z squared plus y squared plus 1 is greater than 1. Therefore alpha is greater than 1. Secondly, we define beta to be equal to sine phi squared. We see that sine phi squared must be between 0 and 1, so beta is also between 0 and 1. Our final, simplified expression is of the form u squared times v squared over c to the fourth is greater than alpha over beta. Since alpha is greater than 1, and beta is between 0 and 1, then the ratio alpha over beta must be greater than 1, which leaves us with u squared v squared over c to the fourth is greater than 1, or in other words, u times v is greater than c squared, which means that either u or v is greater than or equal to c, once again an impossibility. Therefore, the electric force must be greater than the magnetic force, even in the most general case. Now that we have a good understanding of how forces behave in this example, let's discuss how it differs from the example given in section 3.1 in the notes. Firstly, in our earlier example, all charges are considered to be point charges, whereas in section 3.1 there is a distribution of negative charge within the wire. This means that when moving between frames, we need to consider relativistic effects on the charges themselves, such as length contraction, something which is irrelevant in the example studied previously. Secondly, in section 3.1, the density of the positive ions becomes greater than that of the negative electrons, making the overall charge of the wire positive, which generates a positive electric force on the electron. With the two charges, however, they must have the same charge, since the electric force is repulsive. Finally, in example 3.1, we can easily see that there is never any repulsive force at all. Whether the force is magnetic or electric, it is always attracting the electron towards the wire. However, in this example, the components of the force can be either attractive or repulsive, although as we've seen, the overall force can only be repulsive. So, let's go over what we found. The paradox we found at the beginning has been resolved mathematically, as we've seen that in order for the force to be attractive, the speed of light must be exceeded, which is impossible. We found this to be true for the two cases we studied, and we've highlighted some of the key differences between our case and section 3.1. Obviously, there is more work to be done on this topic. In future research, it might be interesting to determine mathematically if the magnitude of the force is conserved, as well as the sign. Thank you very much for watching. We hope you enjoyed this presentation. Over c is greater than x squared over y squared plus 1. No, hold on. And gives us a final result of x minus ut squared over z squared plus y squared plus 1 is over y plus 1 to the fourth root must be greater than 1. No, they're different, because they're the different